record. So now we will do simple assembly instructions. We studied about registers and how the data, especially the integers, are saved in registers and memory. That's one question done. Now let's study simple instructions. So first, the basic instruction is move, and as the name suggests, it moves or copies the value from, for example, operand 1, operand 2. What does operand mean? Operand 1, operand 2. Operand 1, operand 2 means that these are like kind of variables. Operand 1 can be just a register, so for example, an EAX, or a segment register, which is also a register, or memory location. For example, I don't know, if there is a variable X, so operand can be either a register or a memory location. So move can only work if operand 1 is EAX or a memory location, and operand 2 can be anything like a number, that is immediate value, or a register, or a memory location. So a basic example of move instruction can be move EAX, 5. So we move 5 value to EAX, but default value of 5 here means 5 in decimal format. That's the default. If we want to put hexadecimal, we put H in front. So 5 in hexadecimal. Let's try 5 in hexadecimal. So what happens here? So it EAX register, which is basically 4 bytes. These are the 4 bytes, and it gets 5 hexadecimal. So it's already in the hexadecimal form. So it will be 0, 5, 0, 0, 0, 0. Here it will be question mark, because we don't know what is there. Question mark. We'll just get 5. But for instance, if we try to, so if we have some variable x, which is a double word, double word is also 4 bytes, basically 4 bytes. And its value is 5h. So what will happen here? So if we try to move now x, whose value is 5h, in double word format to EAX, what will it do? Now here, as it's already in double word form, it would not have question marks. It will already be 0, 0, 0, 0, 0, 0, because we already declared it in a double word format. When we declared in a double word format, this declaration is always in a memory. So when we declare it in a double word format, what will it become? This is x, so address x, 05, 00, 00, 0, 0, just like the last lecture. In the memory, it's always the opposite order. So in the memory, when we declare something, it's like this. So this is how normal code works. First of all, we declared it in memory as the variable x in the form of double word, that means 4 bytes. And this is the actual hexadecimal value. So in the memory, it will be in the opposite order. But if we move this variable, this memory location, to a register, it will go back into the normal order to 00000005. So this is how move works. It What it does is basically copies the value from operand 1 to operand 2 to operand 1. So 5h to EAX, and here again the value of x to EAX. That's what move does. Secondly, let's try. This was the first move operand. Now let's try second operand. Second, before that, there are um, more types of move. So move SX and move ZX. So see what this question mark problem we faced here. To solve this problem, what we can do is we use special type of move functions. So move SX means that it extends the sign of the variable. So if instead of doing, so we had mov EAX and 5h. So we are moving 5h value to EAX. So usually it would be like this because we don't know what is in EAX. So it will be all question marks. Even this will be question because we are just moving 5h. So what will happen is that when we use move SX, it sign extends the value to the full register. So sign extends means, so for example, if we have 5, its sign extends. So if the sign was positive here, which is noted by zeros usually, so if the sign is positive here, its sign extends to all the to the full register. Similarly, move ZX, now instead of sign extends, it 0 extends. So it will do the same thing, but with sign extends is that the only difference is that it can even work with negative values, minus 5h. So let's try to move minus 5h without first of all without SX. So minus 5h, minus 5h is not possible in hexadecimal. In hexadecimal, minus 5h will be, so minus 5 to, let's convert minus 5 into the from decimal to hexadecimal. So in hexadecimal, it will be, first of all, we write it in the form of, let's do it with 1 byte first. So let's write it in normal hexadecimal, positive hexadecimal. Then we subtract it from one extra value. So here it's 16, here is 15, here is 0. 16 minus 15 is 11, and 11 is, so 10 was A, so B was 11. So B, H, and 15 minus 0 is just F. So here we will move FB, oops, FB to EAX. Slight difference here, important to note. In, we cannot directly move something that starts with. So if a hexadecimal starts with a letter, we cannot move it directly. We have to put a number that is zero in front. It's a very important to remember. We have to put a zero in front. So that's how. So if we work with just move, then what it will do is just do like this FB and zero question mark because we don't know what is there. But if we do move sign extend to EAX and 0FB, which is basically -5 in hexadecimal. Sign extend means that it will extend the sign. So it will extend the F values, which represent that it is negative. FF, FB. On the other hand, if we will do 0 extend EAX, 0FB, H. So instead of extending the sign, it will extend the number into the whole register in the form of zeros. So this will remain, the first byte will remain the same, the FB, which represents -15, but instead of extending the sign, which is F, it will extend the zero. So that's what it means by zero extend. So this is the basic instruction more. Now let's talk about exchange. So it swaps the values of operand 1 with operand second. So if EAX is 1 and EBX is 2, it will swap the values. So it's direct, straightforward. Now let's go to increment and decrement. Increment and decrement. So the format is written like this. Increment operand, that means it will increase whatever that is written here by 1. So if there is EAX, so it will increase EAX value by 1. And similarly with decrement as well. Let's quickly move on to the fourth, that is add. As the name suggests, it adds values. So a simple way it can add is add EAX, EBX. What it does is adds uh, EBX value to EAX and it is saved inside of EAX. So it is saved inside of this first operand. So EAX will be basically EAX plus EBX. That's what add does. And then subtract, it's the same thing. So EAX, EBX, and EAX minus EAX will be EAX minus BX. And yeah, this is like very simple calculation. Now let's try to study what is going on in this code because that's what we will do in the midterm as well. So first of all, we are declaring, so X is a byte, which is 15. Y is a byte, which is -3. And Z is a word, which we don't know what it is. So how will it be? So when we are declaring something, it will be saved into memory. So how will 15 be saved? So in 1 byte is 1 square, and 15 in terms of hexadecimal is 0. If -3 in terms of hexadecimal will be Let's try to convert it for practice. So minus 3. Let's slide the positive value and subtract it from here. 16, 0. If we try to subtract the 16 minus 3 is 13, that is D. And we cannot subtract from 10. Actually, we have to subtract from 100 because we are doing this for a byte, for a full byte. That's why we have to get uh, this as well. So here it will be 15, here it will be 0. Because if we just do like subtract with just 10, with just 16, it will be just D. D can be also 13. So that's why we have to do it in 2 bytes because that's how we will know if it's a negative number or not. FD. FD. This is FD. And Z is a word, so two bytes, 00 and 00. So what is going on here? Mov AL X. What was AL? If you try to remember, EAX had 2 parts, this and this. This was AX, and AX had 2 parts, AH and AL. And why did we use AL here? Because the size of the X is a byte. And we always use the same size. We always use the same size. So if this is a byte, we have to move it in a byte. And AL is 1 byte. That's why we used AL here. So what will happen to, so we will have AL here and AL will be 0F. And add ALY. And if we add Y value minus 3 to 15, you can see that what happens to AL is 15, F minus 3 will be 12, which is C. And what we are doing then is we are moving with sign extend AX, AL. So what we are doing is we are sign extending AL value, which was 0C, to AX, which has 2 bytes. So 00 and 0C. You can see that's why it's here. And then finally, we are saving this value to Z, that is in memory. And whenever we save in memory, it swaps its positions. That's how simple calculation work. And now let's create a new page. All right, let's try to see these instructions. So CBW, what it does is converts byte to word. CBW. So what it means, CBW. It converts byte to word. And which byte? CBW is always works on EAX registers, but what is a byte in an EAX register? So EAX is altogether 4 bytes. AX was 2 bytes, and AX was also divided into 2 parts, AH and AL, which is 1 byte each. 1 byte, 1 byte. What it does is converts, so byte to word. So whatever that is in AL, it converts into full AX. So convert byte to word, that's what it does. So if we have some, for example, 0, 2 inside of AL, what it does is converts it into word, and word is 2 bytes. So AX, now what will it have? 0, 0 and 0, 2. Yeah, but first AX had question marks here because we didn't know what it had. So we couldn't use this directly, but we can use this AX now directly because it has 0, 0, 0, 2. That's why we use these kind of um, instructions. Now CWD is very important. CWD, what it does is it extends AX to EAX, not EAX, it extends AX to DX and AX. This will make sense later when we study the division instruction, but it converts AX, its sign extends AX to DX comma AX. So what it does is if AX has, F, what is AX? AX is 2 bytes, so FF and FD, which will be basically 16, 16 minus A, B, C, D. D is what? C, B, A, 10, 11, 12, 14. And how did we get this? We did 16 minus 3 to get this. That means it will be minus 3. So if this value is minus 3, what it does is basically extends this sign, which is FF, to dx. So like this. So this is dx, this is AX, FF, FF, FD. This is basically convert word to double word, CWD. There is another type of convert word to double word. You can see here, convert word into double word, but it has E in the end. It means it converts AX to EAX. Instead of DX comma AX, it converts AX into EAX. Basically extends word, which is 2 bytes, into double word, which is 4 bytes. 4 bytes. Yeah, these are the examples. So for example, alpha is a byte, and we can only move into AL because AL is a byte. So if we try to represent AX, this is AL and this is AH. So AL will get this minus 2 value, so FE, and convert byte to word. So what it does, it extends the AL value, AL sign, to the full AX. Similarly, if we move this word data 18, so in terms of hexadecimal, it will be 0012. If we move it into AX, we can only move it into AX because it's a word, and that means it has 2 bytes. So 2 bytes is like this. It converts this instruction converts word into double word. This word into double word. It extends the sign, which is 0. So like this. Finally, this also. This is double word to quad word. So instead, it extends EAX to EDX, comma EAX. So if EAX is this, it extends EAX to EDX, comma EAX. So CDQ converts double word to quad word. And then there is negative, it changes the value to negative. Now IML. IML is very important. So IML. So what the mul is unsigned multiplication, IML is signed. We usually always use IML. So what it does is, for example, it multiplies whatever that is in. So if we are multiplying, for instance, AL value, not AL. Let's just suppose it's CL. So what will it do is it will multiply CL with the similar operand of the same size, which is AL, and store the result into AX. So if this will be a IML, if there will be a, for example, a word which is 2 bytes, if there will be a word, it will multiply this 2 bytes with 2 bytes, which is AX, and save it into double the size, which is dx, comma AX. So you can see here, performs a multiplication of the operand. So operand is this, with the register AL, AX, or EX, depending on the size of the operand. So this size will be the same of both of these things. So if it's a word, it will always be multiplied with AX. If it's a byte, it will always be multiplied with AL. If it's a double word, it will be always be multiplied to EAX. And the results will be also, so if it was multiplied with AL, the result will be in the full AX. If it was multiplied with AX, the result will be in this full. And yeah, so the size of the result is 2 times the multiplication. This is how multiplication works with one operand. Now there are other types of multiplications as well. These will be more useful as they are less confusing because we can the result size is the same. So here it works similar to add. So if we are writing EBX and EAX, it saves the result in EBX and multiplies both of them. So this is simpler. Now IDIV is slightly complicated. It works similar to IMUL, IDIV. So IDIV works similarly if we want to divide, for example, a byte. Here is a byte, or let's just say VL, which is a byte, because if there is EBX and it has a half is BX, and which is divided into BH and BL. So if we divide something with this byte, it will always divide it with another byte, which is in the form of AL. Or actually, just so divide ADX by the source operand, store the result. Let's work with word for a second. Just see word for a second. So let's work for a word, like this example. So if we want to divide bx, which is a word, it will divide it with double the size, which is dx, comma dx. So it will divide this with the whole this thing. and the result will be stored like this. So dx will have remainder and ax will have quotient. It is slightly complicated, but yeah, good to know. Slightly complicated. But you wouldn't need to code this, you just need to know how to read. So let's try to read this code. So what we are doing is we are copying x to ax. So let's try to decode this. So ax has now, so if we try write ax, it has half ax and ahal here. So let's try to write ax here. So we are copying x into 16-bit register AX, and the X was word 17. 17 in terms of hexadecimal is 11. If we try to divide this, we will get 11. So what will happen here? We will get 11 in AX, and the sign is 0, 0 because it's positive. And what is CW doing? It's converting word to double word. It means whole of EAX will now get this value. So 0, 0, 0, 0, 0, 0, and 11. Now we are dividing idiv y. Y is a word. Idiv word y. Word was y. So word is divided the similar type, which is also word, or double the size actually. So word will be divided to dx comma ax. So dx comma ax divided by y. What will happen? Dx will get a remainder and ax will get the quotient. And whatever the quotient will be. So what we are dividing 4 to 17. The quotient will be 4. So ax will have just 4 value. And then we are saving this ax to bx. So 4. And then we are moving. So bx we can write bx as 4. And we are copying z value. Z is 5 to ax. Ax has z, which is 5. And CL has 3. Now what we are doing is multiplying CL, and CL is always multiplied with the same size in form of EAX, the accumulator operand. So AX times CL. So AX will save this multiplication. So 5 times 3, that is 15. Finally, now what we are doing is subtracting BX minus AX. BX had 4, AX has 15, so 4 minus 15 is minus 11. And we also need to save it to W, which is a double word, but we have to convert it into double word first. And how to convert it into double word? We either sign extend it or we use convert word to double word. That will convert, and then we will move this EAX value to our memory field, which is W. So that's how we decode simple calculations. One more simple calculation we can learn is about pop and push. These are common simple instructions which pushes the value on top of the stack, and pops the value out of the top of the stack. So push EAX means it will push the EAX value on top of the stack, and pop EAX will take the value from top of the stack and save it into whatever that's written here. That's push and pop. So if we now try to look at the test questions, now we might be able to solve them. So for example, here, general purpose register EAX contains code. So EAX we can write down as 0000 A7FB. That will be a very big value if we try to. So EAX has this. Now what we are doing is we are adding 4 to EAX. So we are adding 4 to this value. Now how do we add 4? So B is basically, it was B. Uh, yeah, B is 11. So it will become 15. So if we add 4 here, it will become A7 FF 0000. After adding 4, now what we are doing is we are moving 0 FFH to AH. So what is AH here? So as you know, this is AX. That means that this will be AH and this will be AL. What we are doing is we are moving FF value to AH. It means then this will become 0000 FF FF. And then what we are doing is we're adding AX. We are adding 15 to AX. So what will be the decimal value of the register AX? So it's just asking about AX from us. So if you look at AX is F, 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 which is -1. And if we add 15 to AX, it will become 15 minus 1, which is 14. So decimal value of register AX is 14. And how do I know if it is -1 or not? You have to visualize. So first of all, if it's FFF until to the end, that means it's negative. It's a negative value. And then we see how far is it from 16. So if it's 15, what we do is we basically subtract 16 from this. So F is 15. 15 minus 16 is -1. That's how we get -1. Or we can even try to visualize, if here was a 16, how do we get 15 here? We just subtract 1. So that -1 is our value. -1. That's the value of AX. And when we add 15, we get the value 14. That's the first question from general instructions. Now we can try this question too. What are the value of EVX and EDX after instruction? Let's write down EDX and EBX. So EDX got 256 and we pushed EDX value to stack. We can create a sample stack here. So 256 there is. And we moved -10 to EAX actually. So let's write EAX as well here. So -10 and add EAX, EDX. EDX is 256. When we add the value of EAX changes, 246 it will become. And then we push EAX on top of the stack. So if this is a stack, let's move this. Now this is the updated stack with 246 on the top. Then we pop the value from the top of the stack to edx. So now this will have 246. And then when we pop, this value goes away. And then we pop again, the edx value will become 256. So the result will be edx will be 246 and ebx will be 256. I think the answer here is wrong. Check. So we moved 256 to edx. We pushed then this value to on top of the stack. Then we moved eax minus 10 to eax. Then we pushed eax value. Ah, let's try this again. So edx, evx. We just have to write what's going on in the registers and in the stack. We have to update with every single instruction. So move 256 to edx. We got 256 here. Push edx. So we got 256 on top of the stack. And then we move minus 10 to eax, minus 10. And then we push eax as well. So on top of the stack, now we will have minus 10. So let's move this down. Now on the top of the stack, we have minus 10. Now what we are doing is add edx value to eax. So new eax will be 246. And now push eax as well. Now we push this value on top of the stack, which is 246. And then we pop the first value to edx. So edx will get 246 and then ebx will get the second item on the stack, which is minus 10. This answer is wrong here because we didn't subtract it again. We didn't, there is only one, in the end we can see. So what we are doing in the end is add to ebx the value of edx. So the latest value of edx is 246 and when we add, it changes to 236. Yeah, that's now correct. So now it's 236 and 246. So we have to see with every single step what's happening. That's how we can decode this. That's how we get the results. So basically we are done with the first two types. Loops will be slightly easier and yeah, these two next will be easier and this will be slightly more difficult.